Were you able to keep up with that last example, guys? Malak and Thuraya and Nujud? Okay, that's good. All right. Just feel free as well if you felt that your internet was lagging and you want me to re-explain things. Just let me know and I'll do that. All right. Okay. Okay. So let's see. Uh, Conservation of energy in a transformer. Now this comes up with the second formula. Now in the second formula, guys, I'm just going to erase this and I'm going to tell you what is the meaning of conservation of energy. Now, most of the time, they say that transformers are 100% efficient. Okay, 100% efficient means that the power input is equal to the power output. Now, in reality, uh, this is not the case. Now, a transformer can be 95% efficient, but for simplicity in calculations, we're going to say that it's 100% efficient. Whenever it says that a transformer is 100% efficient, it means that P1 is equal to P2. But P1 is equal to V1 I1. If you remember the formula, P equals to VI, which is electrical power that we talked about it once upon a time. P2 is V2 times I2. Now this is your second formula in transformers. The first one was V1 over V2 equals to N1 over N2. The second formula is V1 I1 equals to V2 I2. Now, where do we use this? We use it, for example, to answer work to example number 2. If it states that a step-up transformer has an output power of 1000 watts. Now, they already gave us the output power. Output power is P2. So P2 is 1000 watts. If the current in the primary coil is 25 amps, current in the primary coil is I1, 25 amps. What is the input EMF? We want to find V1. Okay? So, let's see. We have P2, which is 1000. I can say P1 equals to P2. So P1 equals to 1000. But I know that P1 can be written as V1 I1. V1, I don't know what's V1. I1 is 25 equals to 1000. V1 is 1000 divided by 25, and 1000 divided by 25, 5 by 1, 5 by 4, that is 40 volts. Okay? It's 40 volts. This is how we use the second formula. There are two very simple formulas. We can actually link them together as well. And we'll see how we can do that. Okay? Alright, so far so good. Okay, great.
Mister, does P1 equals V1 I1 and P2 equals V2 I2?
Yes.
So does that mean that like PT equals VT, like total power equals total? Like when we come to like separate the formula and like we want to get like the total power, do we add P1 and P2.
Now the total power, because if you're talking about the total power, yeah, you're gonna add P1 plus P2, but right now you're talking about the input versus the output, because there is a power input and there is a power output. All right. So the total power
Because I
is
don't
not
get what the
P1.
second term is.
Now listen to me.
Is it P1 equals P2?
The idea is that, yeah, it's P1 equals to P2, but the total power is not P1 plus P2. The total power in the transformer itself is, for example, in that case, is 1000 watts. It's like a total power input to a transformer is actually output the same. It's also 1000 watts. So that's the total power.
Alright, thank you, sir.
All right. Now, if I can go to efficiency of transformers. Now, sometimes a transformer is not 100% efficient. Now, we assume that it's 100% efficient, but in most of the cases, it's actually not. It's actually up to, as I said before, 95 up to 90% efficiency. Now, for example, if I gave you this example, just give me a second before going to efficiency. Let me try to explain what efficiency is. Now, for example, if I said that a transformer is 90% efficient, okay, if it's 90% efficient, you cannot say P1 equals to P2. No. Okay? No. You cannot say that. But, for example, if I said, I already gave you V1 to be, let's say 200 volts, and I1 to be, let's say 0.5 amps. And I said, okay, V2 is 50 volts, find I2. With this transformer, which is not 100% efficient. Now, how can you do this? What you would do is you would use these two to find the input power, which is going to be 200 times 0.5. This is 100 watts. Okay? Now, when I say 90% efficient, to find P2, P2 is 90% of P1. And 90% of P1, which is 100, okay, is equal to 90%, not 900%. That's a 90 watts. Okay, so you already now know that P2 is 90 watts. Now coming back to this part here. If I know that P2 is V2I2, 90 equals to 50 I2, 90 over 50 equals to I2. What is 9 over 5? That's a 1.8 amps. Okay? 1.8 amperes. Good? All right. Now, okay, was the last example clear, all of you? Do you have any questions before we proceed? Everything clear, guys? Yes. Okay. Good. All right. Hassan, Umar, and Thuraya, everything okay? Okay. All right, everyone. Now, there is an important thing that you need to note, which is if I want to increase the efficiency of my transformer, I need to use low resistance coils to reduce the power waste due to heating effect of current. Okay, reasonable. Using a laminated core, which consists of layers of iron separated by layers of insulation. This reduces heating in the iron core and prevents currents being induced in the core itself, referred to as eddy currents. Now, eddy currents are not in the syllabus, but they're one of the factors that causes transformers to be not like they lose their efficiency a little. So these are the two things I want you to note. Use low resistance coils. Use a laminated core. Now, when you say laminated core, laminated iron core, it looks like that. Okay? It looks like this, guys. The iron core itself. Okay, it's made into layers. It's not a single iron core, look. Alright, it's layers, sheets of iron together. Okay, this is lamination. It's not just sheets of iron, you need to understand it's one sheet of iron, okay, and one sheet of insulation. Iron insulation. Insulation can be plastic, it can be anything else, but this is a laminated core. Look at it. Alright? Now you understand what a laminated core is. Okay? It prevents the iron core from heating, and it prevents the iron core to induce current in it, to carry current. Because if the iron core carried current, some of the current is not going to go to the secondary coil. So these are the two things that you need to note down to increase the efficiency. Use low resistance coils and then use a laminated core. Okay, please copy that down or take a screenshot before we proceed. Okay, are we ready to move on? Okay, are we good? Can we move on? Did you copy that? Or did you take a picture?
Yes.
Okay, good.
Mister, can you go back again?
Okay, yes, I can. Okay, these are the two important points that you need to note. Let's take a quick picture before we proceed.
Okay, thank you.
All right. Now, why do we need transformers? Okay. Now, the main idea is we need them because of two main things. Now, electricity companies, it says that they are keen to eliminate any waste. If electrical transmission cables heat up, energy is not making it to the consumers. Therefore, it cannot be sold for profit, and inefficient transformer wastes power and money. Okay, what is that supposed to mean? When transformers increase the voltage, the current in the cables is lower. Okay, when transformers increase the voltage, they reduce the current. Because if you remember, let's just put it to a quick test. Let's say that I have a transformer that V1 is 200 volts, I1, let's say is, I'm gonna say 10 amps. If I increased V2 and I stepped it up to 1000 volts, what happens to I2? So I stepped up the voltage and I want to see what happens to the current. Okay, so if I said V1 I1 equals to V2 I2, 2000 over 1000 equals to I2, which is 2 amps. So what happened to the current? The current was reduced. Okay? The current was reduced. But why? Why do I need to reduce the current? Because we know that in a wire, if current is flowing and a wire has a significant resistance, okay, the resistance causes a heating effect. The resistance of the wire causes a heating effect. So that the electrical energy from the main power station does not reach the consumers. Some of it is wasted, okay? Some of it is wasted due to the resistance, okay? How can we minimize this energy wasted? Because the energy is wasted. The more the current, the more energy is wasted, the more the heating effect. We talked about it. We talked about the heating effect of resistance. If we increase the current, the wires heat up more. So that's why we need to reduce the current. How do we reduce the current? By using a step-up transformer. The current reduces from 10 amps to 2 amps, for example. That's the main idea. So mainly in power stations, what they do is they have a step-up transformer. They step up the current. They step up the voltage so that they can transmit the electricity through long distances from the main power station to the cities, to the sub-power stations, to the consumers. When it reaches the consumers, they can step it back down again. Let's go back and see. So, what I just explained is transformers are designed to increase the voltage at which electricity is transmitted. The advantages of such high voltage is that the current is lower and less energy is wasted as heat. In addition, the cables used to carry the current have a large cross-section area, and this lowers the resistance and energy wasted. Remember, cross-sectional area means less resistance. The greater the cross-section area, the lesser the resistance. And the lesser the resistance means less energy is wasted. That's why the cables are actually thicker. Okay, now this is the figure which explains how a power station transmits electricity to the consumer. So It goes from the power station through a step-up transformer. In that step-up transformer, it steps up the voltage to reduce the current. Why? Because the current needs to travel long distances. Okay? So we don't want energy to be wasted here. That's why we step up the voltage so less current flows. So less current flows here. And when it reaches the consumer, it uses a step-down transformer that decreases the voltage. Current comes back to its original value. Then the consumer uses it. Okay? We always use an AC supply, AC current, because transformers, they don't work with DC, because as I explained last time, transformers, for them to work, they need a changing magnetic field, and a changing magnetic field is only supplied by an AC current. So if we use the DC supply, that's a constant magnetic field, which is not going to work with transformers. Okay? All right. So, now, all right, so before we proceed, is everything clear?
Yes.
Yes, this last part is very important, the part where we transmit electricity from power stations to consumers, and why do we need transformers here is very important. So you need to ask questions if you didn't understand anything here. So please, your questions. If everything is clear, just say clear. All right. Okay, good. So let's see. Okay, that's 9 minutes video. Let's see if we have questions. Questions. Oh, wait a minute. I need to go back and where does it say? Okay, just give me a second. Alright, electromagnetic effects. Okay, transformers. Questions? Alright, please with raise of hands. Which of the following parts of the transformer is the input AC supply to? Okay, Sama?
The primary coil.
Primary coil. Good, Sama. Good. Calculate the voltage on the secondary coil. If the voltage supplied is 20 volts, the number of turns in the primary coil is 100, and the number of turns in the secondary coil is 600. Do your calculations if you have a paper in front of you, and when you're ready with your answer, raise your hand.
Mr. I can't see the question.
You can't see the screen, Hassan?
I'm gonna leave and join again because it's not loading for me.
Alright, do that, please. Okay, Lena?
120.
120 volts. Correct. 120 volts. Okay, if you don't know how we got the 120, please ask. If it's okay, we move on. The power supply to the primary coil is 45 watts at a voltage of 9 volts. Calculate the current in the secondary coil if there are twice as many turns on the secondary coil than the primary coil. Oh, that's a good one. I'll give you a couple of minutes. When you're ready with your answer, raise your hand. Nobody?
Wait, mister, I'm working on it.
Okay. Or Thuraya, you want me to explain the previous one?
Yes, please.
Okay. I'll do that. And I'll give you a chance in the time being for the rest of you to answer. Okay, previous. Let me just see if I can go back. How can I go back to the I can't even remember the previous question. Okay, Thuraya, we'll go back to it in a bit. Okay? Cool? Alright.
Mister, I just need your help in just like one step. How do we calculate the number of turns? I think I missed that part.
Oh, the number of turns. The formulas that you have that I taught you are V1 over V2 equals to N1 over N2. We know that V1,
Okay.
when they say that the number of turns in the secondary coil is twice, it can be 1 to 2.
But how do we know the number? Like, what if like the primary coil? How do we know it's one? Maybe it's more than one.
It doesn't make a difference. If it's 40, the secondary coil would be 80, which it will simplify again to 1 to 2. If it's 1,000, The second one would be a 2000, and it would simplify to 1 to 2.
Okay, thank you, sir.
So V2 is 18 volts. All right? And they gave us that P1 is 45 watts. And according to the efficiency of a transformer, P1 is equal to P2. And P2 is V2I.
Mister, is it 2.5?
Let's see. 18I2. So I2 is equal to 45 over 18, which is a 2.5 amps. Yes, 2.5. All right. Okay. This is the value of the current in the secondary coil, which is 2.5 amps. Okay. Before we proceed, let's see your inquiries. All right, guys, what are your inquiries, people? I'll have you take a look at it again. If you have any questions, let me know. All right. All right, Najud, which part do you want me to repeat? Just unmute yourself and let's just discuss it together.
All of the question.
Okay, the question says find the number of turns in the secondary coil. Yeah? Which is I2, yes. And I2 is 2.5. So we already know that V1 is 9 volts, but we don't know V2. Okay, we don't know V2. We don't have N1 and N2, but it says that what you need to understand is when they say that the number of turns is twice, we can directly know that the voltage will also be twice. They're proportional like that. Twice the number of turns is twice the voltage. Or as we use the formula here, we got that the voltage is equal to 18 volts. Okay? Does that make sense here at the beginning?
Yes.
After that, we want to find I2, and I2 is found by using the formula, this one. Okay? We already know V2. We already know P2 because P2 is equal to P1. They already gave us that P1 is 45 watts. If P1 is 45 watts, P2 is also 45 watts. And we use the formula P2 equals to V2 times I2. Then I just substitute it. P2 is 45, V2 is 18, and I2 is here. And finally, I2 is 45 divided by 18. And 45 divided by 18 is the 2.5 that we got here.
Why is P1 equal to 45?
P1 is equal to 45 because they said the power supplied in the primary coil is 45 watts.
Okay.
Cool?
Yes.
All right, great. Complete the following sentence. The transformer core is made of dash because it allows magnetic flux to access the secondary coil.
Iron core.
Iron.
Iron core.
Okay, good. That was an easy one. Which of the following is a benefit of using high voltages to transmit electricity? Let me see. Okay. All right, Lena.
Number 1.
Number 1, less heat is generated in transmission. Good. A step-down transformer is 80% efficient. Sorry. They gave us the voltage in the secondary coil, the current in the primary coil. They want the primary voltage. I'll give you some time to answer this, and when you're ready, give me your answers.
Mister, I got 19.2.
19.2. Let's write it down. Oh no, it's not 19.2.
Can I try again?
Okay, keep trying. Keep trying. Okay, I'm going to ask.
Mister, can you try 56.25?
56.25. Let me see. 56.25. No. Okay, we have Lena.
120.
Lena said 120. And Lena is correct. But how did we get this 120? Okay, efficiency is 80%. Okay? V2 is 24 volts. I2 is I2, where is I2? I2 is 2 amps. And I1 is 0.5 amps. We want to find V1. Okay? V1 is the problem. Okay. Now, that was a tricky question. It's a very tricky question, but when they say an efficiency of 80%, I'm just going to give you a shortcut. an efficiency of 80% means that the relationship between P1 and P2 is P1 equals to 80% times P2. No, that's the opposite. It's P2 because P2 is the lesser one. Okay, P2 is 80% of P1. Good. P2, I'm just going to write it as 0.8 P1. If I have V2 and I2, I can just say P2 is 24 times 2. 0.8. P1 is V1I1, which is V1 times 0.5. Okay? 24 times 2 is a 48. 0.8 times 0.5 is a 0.40. Okay? V1. Good? Finally, (48) divided by 0.4 is V1, which is 120 volts. Okay? The main idea that I used here was P2 equals to the efficiency, and this is the symbol for efficiency, times P1. Okay? When they say that it's 100% efficient, it means that the efficiency is just 100 over 100. That's why we say P2 equals to P1. Alright, so that's the main idea. Okay, take a look at it. Just going to give you a chance to understand what I just did. Alright.